Swayam Prabha. Digital India. Educated India.
So welcome back everyone, and in this module we will be discussing about an important example of the case of Rutherford's experiment. Okay, so let us now recall what was the Rutherford's experiment. Let me call this as RE. So I don't want to write all the time Rutherford's experiment. So the experiment was that there was a beam of alpha particles. Alpha particles are typically positively charged particles, example proton. So beam of alpha particles were scattered by a gold nuclei on a sheet of gold, right? On a sheet of gold. And what we saw was typically gold was chosen. So gold was chosen because gold has a very high molecular weight. So it was a heavy atom, right? So it is expected that a heavy atom will be able to deflect a beam of alpha particles, which are of course significantly lighter than the gold nuclei, right? And earlier we will see over the course of our discussion that how the Thomson's model was rejected. Remember, Thomson's model was that Thomson's model hypothesized that the atoms in the electrons in an atoms are evenly distributed. So it is as if the electrons are orbiting the nucleus in such a way that you can treat the entire atom as a homogeneous solid sphere. So atoms are evenly distributed. So that was what the Thomson's model predicted. But eventually through Rutherford's experiment, we came to know that atom is mostly empty. It is only a very small portion of atom which is concentrated in mass, which is at the roughly at the center, which is the nuclei, and rest of the atom is empty, right? So that was a completely fundamental change in the thought process of the shape of atom, and we will see just now how it was materialized, right? So the beam of experiment was the beam of alpha particle was scattered through a gold nuclei. So what we had is, now we are going to slowly set up the mathematics for this example, for this experiment. By first, we first simplify the scenario by looking at the deflection of one alpha particle with one gold nuclei, and then we are going to generalize the system with a beam of alpha particle to a sheet of gold nuclei, right? So let us now first look at a simpler example here. So we have an alpha particle where so let us say our gold nuclei is sitting here. So just one gold nuclei, and an alpha particle is alpha particle is given by this quantity A. So a particle is approaching the gold nuclei through a beam, and the moment it and the perpendicular distance of approach is P, right? And then the moment it approaches the nuclei, remember both are positively charged, so we expect that this alpha particle is going to be deflected by this gold nucleus, so they are going to be deflected, right? And then of course the motion follows one branch of a hyperbola, so we have these following geometric quantities alpha and our deflection angle theta, such that theta is pi minus 2 alpha, right? So now let us further give some more details. So we have an alpha particle A of mass m and charge q, right? It approaches the gold nuclei B, and B of charge capital Q, right? So initially at t equal to 0, B is at rest, and A is moving with speed V along the line perpendicular to the alpha particle is moving with a speed v, so this speed is v at t equal to 0 along the line perpendicular to the distance to the line of approach. Okay, so I'm talking about this distance p, the perpendicular distance. Okay, so then the force on A, the force exerted on A by the gold nuclei, right? So force exerted on A will be what is it? So will be, remember it's a central force. So we are talking about, so this is my radial coordinate r. So the central force F of r is given by Q times capital Q divided by r square. So we are talking about a central repulsive force acting on the alpha particle. And to find the goal of our problem is we want to find the deflection angle. To find deflection angle theta, this theta, right? And we note that in this case our constant gamma, remember we are no longer talking about planetary motion here, we are talking about distances of the order of angstrom. So gamma this time is Q times capital Q divided by small m, right? So this is a small quantity. And now we use our L formula, the angular momentum conservation. So at t equal to 0, our angular momentum is p times v of the alpha particle. And this is, so L square comes out to be gamma b square by A. I don't know what is A and B. We'll find it very shortly, right? And my E formula comes out to be v square by 2 is gamma by 2A. Okay. So from here I see that my A is gamma by v square and my B is P. So by solving these two equations, that is what I get. So then recall from the conic section, recall the following. Recall from the conic section that the angle alpha is such that tan alpha is B over A, right? So this comes out to be, tan alpha comes out to be PV square by gamma using this, using star. Okay, so from star. Okay. So now my theta is pi minus 2 alpha, or my theta by 2 is pi by 2 minus alpha. So I put a tan on both sides and I get that this is cot alpha. And from here I can find that this is also equal to gamma over PV square, right? So gamma over, what have we got? Right, gamma over PV square. And I can plug in the values of gamma and we can find that my tan theta by 2 comes out to be QQ by MPV square. So that is my deflection angle theta by 2. So I think in terms of finding the angle, how much the alpha particle is deflected by the gold nuclei, I think our objective is achieved. But the problem in this exercise is that typically we don't know what is the value of P in the experiment. What is the perpendicular distance of approach of the alpha particle? Remember, we are talking in angstroms. And also and also we don't know what is well we don't know what is this deflection angle theta also, right? So this deflection angle is also, so in the experiment this is also unknown, right? Of course, P is all unknown. So basically what I'm saying is, let me call this as double star, formula double star. So formula double star is unusable. Formula double star is unusable because P and theta, which is the experimental parameters, are not measurable, right? It's not at this level of angstrom. There are so many variabilities, including the so-called famous Heisenberg uncertainty principle. These becomes almost immeasurable. Okay, not measurable. Okay, so then what to do then? So then we need to homogenize the system. We need to look at lots and lots of alpha particles, namely the beam of alpha particles which are hitting lots and lots of gold nuclei, which is the sheet of gold nuclei, and then we want to find the average deflection, right? So we average out these values, and that is something we can find. So what have we got here is, so the idea is we now have a beam of alpha particle. So alpha beam, right? So alpha beam, and let us call this as, let us fix some origin of our measurements, let's say O prime, and let us say that the beam is hitting some sheet of gold nuclei, right? So that is what I'm saying. So this is my gold sheet, right? Gold sheet. And what we have is that the beam of alpha particle. So let us take a cross section of this beam of alpha particle. So the beam has some cross section. Cutting a slice of this beam, we will get one area under consideration of the approaching beam, and then when it hits the gold nuclei, it is going to get deflected. And this time there will be many deflections of all the alpha particles. So the net deflection can be clubbed into a so-called cone. So this is my deflection cone. So all the alpha particles are getting deflected in a cone of cone, and we want to find the area of this projection, the projected area of this cone, which is our the quantity of interest. Okay, so this the cone will be making an angle theta with the x-axis, right? So this is my deflection angle, right? And so let me write all these details one by one. So what have we got? Instead of one gold nuclei and one alpha particle, we have a thin gold foil. Remember the word thin. The word thin is used in the sense that the gold foil is roughly 1 atom thick, right? So thin gold foil, which is irradiated with a uniform beam of alpha particles of same energy, uniform beam of alpha particles of the same energy, and we call this as we call this as the so-called monochromatic alpha particle beam, right? So so the idea is the word thin is used to represent one atom thick gold foil, so that there are no multiple deflections. So there is no multiple deflections because there is just one atom which is deflecting from the gold foil. So no multiple deflections. So that is why we need a thin gold foil. Okay, so then now, so with all this setup, so the goal of this new problem is, we want to measure the angular distribution of the scattered alpha particle, the angular distribution of the scattered alpha particle, which is what we are saying, the angular distribution, right, which is in this cone. The angular distribution of the scattered alpha particle, what do we call scattered alpha particle? Okay, and there is a name to this which is known as the differential. I'm not a solid state physicist, so these are also new to me. So differential scattering cross section. Differential scattering cross section. Okay, so differential scattering cross section density, right? So we call this as sigma of n. So again, we are trying, so this is our cone which is getting deflected with an angle theta, and the cone makes a normal to the surface given by n. So this is the n, and we want that this is the cross section with the gold foil that the cone makes. So we want this to be our sigma. So this is our sigma of n bar, and this is the quantity that we are trying to find, the differential scattering cross section. Okay, and n, as I just said, n is the unit vector specifying the direction of emergence of particles from scatterer O. Okay, direction of emergence of particles from scatterer O. Okay, so suppose we have a uniform flux. As I just said, we have a monochromatic beam of alpha particle. So suppose we have a uniform flux of alpha particles which cross the reference frame, the reference frame. Okay, let us call this uniform flux to be A, such that n particles cross a unit area, of the plane. Okay, of the plane A. So these n alpha particles are scattered by the foil. Okay, so this is the number of particles that are crossing per unit area. Okay, so then remember what have we got here? So these n particles will be scattered by the foil, will emerge in a direction along, this is what we are talking about, that the scattered n particles are going to emerge in a direction which is making an angle theta with respect to the horizontal x-axis, right? So so this is the entire statement that I just said. Okay, so then the differential scattering cross section, so in this case sigma of n bar comes out to be the flux of the particle, the flux of these particles will be sigma of n, will be sigma of n. I just don't want this here because it's too cramped up here. So sigma of n times ds. So this is per unit area times ds. We need to integrate, so that gives us the total area or the total flux. So number of particles which are crossing is capital N. So this is my flux of particles which are emerging out, right? So this was per unit area, so we have multiplied with the total area. So flux of particles. Okay. So since the incoming beam is uniform, I see that the flux A, well, I need to keep referring to the diagram. So my area A is this area where the beam is being irradiated. Okay, so the flux A, this is A is also equal to n times the area A, right? Now this flux is the flux which is emerging, right? This is emerging and this is being irradiated, right? So we are throwing this flux in and this is coming out, and both of them must be equal because this is the conservation of mass or conservation of the number of particles. So then further we can assume that the influx area is a circle of radius p1. Basically I'm saying that this quantity capital A is pi p1 square. So I'm simplifying my life here by saying that the influx beam is a circle of radius p1, right? And what we have is that from here what we get is, we can equate these two. I see that this is summation sigma theta, this time theta, because n is a function of theta here, right? So sigma theta ds over the entire surface area S is equal to pi p1 square. So remember, our goal is to find the sigma theta. So sigma theta is related to the incoming area of the alpha particles as follows. So then let us say the scattered flux, as I just said, that the scattered flux is a circular cone, right? So circular cone, and the cone makes an angle theta. So suppose the scattered flux, assume the scattered flux is a cone theta 1 from theta 1 to pi, and integral sigma theta ds is integral theta 1 to pi d theta integral 0 to 2 pi. Remember, we are just trying to integrate this. This is over this is the solid angle here. So I'm talking over the cone. So the cone will subtend a solid angle which is in 3D. So this is going to be theta 1 from theta 1 from 0 to pi, and then we have theta from 0 to 2 pi sigma theta sine theta d phi. Okay, so we have phi being so I need to tell everything. So theta 1 is the 2 pi minus theta, and theta is this angle of deflection, and O is the origin of the cone. And now what we have is that we can quickly, so where is d phi? So d phi, theta 1, hold on. So this is d phi, I think d theta. d theta should have been here, and this was d phi. Okay, so phi from 0 to pi. Just a minute. So, well, something is messed up here. The limits here is theta from 0 to pi, theta from 0 to pi, and phi from 0 to 2 pi. So this is d phi and this is d theta, and from here I can see that this is equal to 2 pi times integral from 0 to 2 pi, 0 to pi, sigma theta sine theta d theta. Okay, so then I can see that this is also equal to what? This is also equal to pi p1 square. This was the area of the incoming wave, and I can write this as 2 pi times integral 0 to p1 p dp. Pi p1 square I can write it in integral form, right? And also I can write this as dp d theta times d theta, right? And then I can see that this is also equal to what? This is also equal to I have changed my angle, my integrating variable to be theta. So now theta will be from 0 to pi, right? And also I want to put a minus sign because it is an incoming wave. Remember, the direction of the beam is opposite to the direction of the deflection. The deflection is along this direction, the beam is along this direction. So we need to take into account with a minus sign here. So all in all, what we have got is, so I have equated these two equations, and I can now equate the integrand because the limits are the same of the integral. I can equate the integrand. I see that equating integrands, I see that my sigma theta comes out to be minus p by sine theta times dp d theta, right? And that is what my differential cross section scattering density is. That is what the goal of the problem is, right? Now in the Rutherford scattering, recall in the exercise that we did earlier to this, recall that my perpendicular distance p was equal to q by mv square tan theta by 2. This is what we found for one alpha particle, right? And we can plug this plug this information we can plug this information in this value p here. We don't know, remember, we don't know what the value of the variable p, but we have this formula. We can plug it in terms of theta, and now my sigma theta comes out to be q square divided by 16e square times 1 by sine theta by 2 to the power 4, right? So this is my differential cross section area. Now let us try and put in some values to see what is happening to this area. So far we have just done some math here. Now our next exercise is to show you the significance of this experiment. Very quick, right? So the significance of this Rutherford's experiment. Notice that the distance of closest approach, this is from some solid state physics details, the Bragg's law. The distance of closest approach at theta equal to pi comes out to be d, which is q by e. E is the energy of the beam, and this comes out to be roughly 10 to the power minus 12 centimeter. So this is the p that we are talking about, the distance of closest approach of the alpha particle, right? And it is further known, it is known that the radii known that the radii of the gold nucleus R is roughly 10 to the power minus 8 centimeter, right? And so this is very big compared to D, right? So this is very big compared to D, which means that the distance of closest approach, which means that uh, uh, basically the alpha particle is not approaching, as if it is not being deflected by the atom. It is being deflected by a very dense mass which is concentrated towards the center of the atom, right? Notice that the distance of closest approach is much smaller than the radii of the gold nuclei, which means that this deflection which is happening for the alpha particle is not due to the atom, but due to something which is very much concentrated at the center of the atom. And that is how the Thomson's experiment got abolished, because Thomson had premised that the atom was homogeneously distributed with electrons. And here we see that the Thomson's model, we see that the atom is mostly empty. So from these values we have come to the conclusion is atom is mostly empty with a small dense nucleus. So this was in contradiction with the Thomson's model, which led to the development of a new model of the shape of atom. Okay, so that was what the Rutherford's experiment taught us, and I think we are out of time for this module to continue. But in the next module, I will continue on another aspect of classical mechanics, namely the case of nonlinear oscillations. So thank you very much so far for listening. Thank you.